Okay, in this video we're going to talk about section 4.4 on indeterminate forms and L'Hopital's rule. So this brings us back to limits. We saw limits, of course, back in chapter 2, and the techniques we used there were generally algebraic or graphic. But in a lot of limits that we'll see in this section, we can't use just regular old algebra in order to solve these. So L'Hopital's rule is going to help us in these cases. But we also want to talk about what types of things we can encounter when looking at limits that we can't quite figure out without doing some work to them. So ones we've seen already, like we've seen 0 over 0. That is, so we're not literally trying to divide 0 by 0 here. What we're saying is that we're doing a limit, and the top goes to 0 along with the bottom. So both top and bottom go to 0. So we saw back in chapter 2 that when that happens, usually meant we could do some algebra to simplify it and still find the limit. So that's why we call it indeterminate, because it could still be something. If the top and bottom go to infinity, and this could be plus or minus infinity, that's also an indeterminate form. And those are the two main ones for L'Hopital's rule. But there's quite a few other ones as well. If you multiply 0 by infinity, and again, that could be plus or minus infinity, then that's another indeterminate form. If you have two functions that you're subtracting and they both go to infinity, that's indeterminate. And we have three power versions. We have 0 to the 0. So if you have a function raised to another function, both of them going to 0. If the base goes to 1 and the exponent goes to infinity. And finally, if the base goes to infinity while the exponent goes to 0. So these are all examples of things that could still have a limit. And we'll see a few of them here, but we won't see all of them most likely. But the idea is that if they're in this form, or if they can be brought into one of these two forms, the fraction forms, then we can use L'Hopital's rule. So each one of these, if you have a product of two functions, you can change that to a quotient. If you have a difference, and if you have powers, we'll see how you can change those to quotients too. So what is L'Hopital's rule? Oops. So we'll start with if the limit as x goes to a of our function f is 0, and the limit of another function going to a is also 0. So in other words, we're getting this form if we have f over g. Then the limit as x goes to a of f of x over g of x. So in other words, if we tried to plug in a, we would get 0 on the top and the bottom. That we can take the derivative of each function and do that limit again. So limit as x goes to a of f prime of x over g prime of x. Now be careful here, because it kind of feels like we should do something like the quotient rule or something, since we have a quotient of two functions. We're not trying to find a derivative. We're trying to find a limit, and we're using the derivative to find that limit. So we do take the derivative of the top and the bottom, and then redo this limit. And you get the same result if the zeros are replaced by plus or minus infinity. So I'm not going to write the whole rule again with infinities in there, but it's the same idea. So if you get 0 over 0 or infinite over infinite, then you can use this rule. So let's look at a simple example first. So let's put a line here. We'll look at the limit as x approaches 1, 3x to the 5th minus 4x squared plus 1 all over 2x to the third minus x minus 1. Oops, minus 1. So if you tried to do this limit by just plugging it in, if you remember how we tried to solve limits back in chapter 2, you try and just plug it in and see what you get. But if you do, you get 3 minus 4 plus 1, so 0 on the top, and 2 minus 1, so you get 0 on the bottom as well. So it is of this indeterminate form. So we can use L'Hopital's rule, taking the derivative of both the top and the bottom. Again, we're not using a quotient rule here, we're just taking the derivative of each function separately. So the derivative here would be 15x to the fourth minus 8x, derivative of 1 is 0. And then on the bottom, 6x squared minus 1. And this 1 is also 0. And now we have no problem plugging in the 1. Plugged in the 1 for each of these x's. And you get 15 minus 8, so that's 7 over 6 minus 1, which is 5. So the limit is 7 over 5. Okay, let's look at one with infinity. I'll just put examples here, so we'll continue on. So limit as x goes to infinity of the natural log of x over x. So here we have, as x goes to infinity, natural log of x also goes to infinity. And as x goes to infinity, x goes to infinity. So this is looking like infinity over infinity. So we can apply L'Hopital's rule and take the derivative of the top and the bottom and redo the limit. So derivative natural log we know is 1 over x, and the derivative of x is just 1. So this is the limit as x goes to infinity of just 1 over x, but we know that this goes to 0. You have a constant over some power of x, that limit is always 0. Sometimes you have to do this multiple times. If you do the derivative top and bottom, sometimes it's still 0 over 0, and you just keep going. Do it again. Let's take a look at one that gives us this example, the 0 times infinity. We're going to look at the limit as x goes to 0 from the right of the tangent of x multiplied by the natural log of x. So it's a product of two functions. And you have to remember what these functions do. Tangent, well, at 0, tangent is just 0, right? So let me not put the equal sign. We're saying this is going towards 0. And natural log, if you remember the graph for natural log, it goes down towards minus infinity, it has a vertical asymptote at 0. So it goes down towards minus infinity. But it is of this form, 0 times some form of infinity. So we want to convert it into a fraction. Well, luckily, the reciprocal of tangent is cotangent, so we can put that on the bottom and say this is the limit as x goes to 0 from the right of natural log over cotangent. So in other words, when we have one of these other forms, we want to turn it into a fraction somehow. Sometimes it's going to be a little bit weird how we force it into a fraction, but other times it's, like in this case, it's pretty natural. So as x goes to 0, again, this top is going to minus infinity. And you may remember cotangent, as you go to 0, it goes to positive infinity, if you're going from the right. So going from the right is important here. If I just said 0, then it wouldn't exist. Actually, it still exists in this case, but it has the possibility of not existing. Okay, so that means we can use L'Hopital's rule, but we're going to use it on this. So we have the limit as x goes to 0 from the right Natural log again, 1 over x. And cotangent, may have to look that one up, but that one's a negative cosecant squared. And before we just throw back in 0, you probably want to simplify these first. We'll see in the exercises that we generally want to simplify these before we just start plugging things in. So what I want to do here is, well, I'll first take the negative out. Let's put the limit in there. So we have a minus sign. Cotangent, or cosecant squared, is a sine squared on the top, and this x is on the bottom. So I can pull one of those signs and combine it with that x that goes in the bottom. And the other sign I'll just leave on the outside. So we can simplify it to this, or rearrange it to this. And I do that because you may remember this was in chapter 3 when we were proving the derivative of sine. We had that the derivative of, or the limit as x goes to 0 of sine x over x was 1. So we actually can plug in the 0 because we get minus 1, but then sine of x, sine of 0 is 0, so 1 times 0. So that's 0. So the limit here is 0. And finally, before we jump into our exercises from the notes, we'll do one more that looks like one of these three. Oh, let me put it down. So these three here, exponential form. I'll try and fit it all in one for the moment. Okay, so it's the limit as x approaches 0, sine x raised to the x squared. So this is an example. If we try and plug it in, we get 0 here. Sine of 0 is 0. And x squared, 0 squared would be 0. So we get this indeterminate form, 0 to the 0. Again, there's 3 possible indeterminate forms that we can work with. And this is one of them. So what do we do in this case? We want to use natural log to pull the exponent down. So if we call this L, so eventually we're going to solve for L, but we're going to call the limit L, and then take natural log of both sides. So we'd have the natural log of L is equal to natural log of this, but the exponent will come down, so x squared, natural log of sine. So essentially this came down. Oh, and we're doing the limit as x goes to 0, so I'll squeeze that in here. So what's that look like right now? Well, x squared would go to 0, and natural log of sine, as x goes to 0, sine is going to 0, but natural log would be going to that minus infinity again that we saw before. So now we've sort of turned it into from this one to this one. And that would happen with all 3 of these. They would always turn into this one. And we saw before when we have something like this, we have to turn it into a fraction. And so in this case, we have to do it in a kind of weird way. Or maybe not too weird. We have x to the 2 on top. We'll just bring it down as x to the minus 2 in the denominator. Now it looks like minus infinity over infinity. X to the minus 2 is really 1 over x squared, so that would go to infinity as x goes to 0. Now we can finally take derivatives of the top and the bottom. So using L'Hopital's rule, the derivative here, using the chain rule, it would be sine over cosine, so you end up with tangent. Let me move this up. And here, just power rule, so minus 2x to the minus 3. And we should simplify that first. So limit x goes to 0. Bring this back up. So x to the third tangent over the minus 2, which isn't going to matter here because everything's going to 0. x cubed is going to 0, tangent is going to 0. So we're once again getting 0. But that's actually not our final answer, because that was the natural log of our limit. So putting that together, we have that the natural log of the limit we're looking for is 0. So we do e to both sides, so the limit is e to the 0, which is 1. So the actual limit here is 1. Circle that twice since we have two things circled. So that's the process for these exponential ones. So you take the natural log first, put it back into a fraction, use L'Hopital's rule to take the derivative, and then find the limit. Now, before I go to the exercises, I want to note that while we have these indeterminate forms, these 7 up here, there are combinations of 0, 1, and infinity like this that are not indeterminate forms. So it's good to recognize that as well. So for example, I'm just going to put not indeterminate. So if you're doing limits and you get, say, two functions that are both going to infinity when you're multiplying, well, that's just going to be infinity. There's sort of no question there, right? If something's going to infinity and another thing's going to infinity, then multiplying is going to infinity. If you have 0 over infinity, that's sort of like doubly going to 0, right? Because 0 on top, and then infinity on the bottom is just making it even smaller. So that's just 0. For powers, if you had infinity raised to infinity, almost the same reason as that would just be infinity. 0 to the infinity. I'll put that here. That's like taking 0 and multiplying it by itself a bunch of times, so that's just 0. And dividing things by 0 normally doesn't exist, right? So that's true with infinity as well. So if you do infinity divided by 0, or really if you did any other number divided by 0, like 1, these both don't exist. It's only the case where you have 0 over 0 that it might be indeterminate for the fractions, or for dividing by 0. Okay, so in the next video we will take a look at some of the exercises, these ones here. But again, try some of these out first. There is a typo with this one. This should be a 2. But you can try it out with the 1 as well. We'll actually probably do both versions in that video. And G. I'll mention how to do it, but that one's really difficult, so I'll probably skip over that one. But the rest of them, I suggest you try out and then come to the next video.